Hi everyone, this video covers the material from section 5.2 in your textbook, which is something we call the addition rule for probabilities. So I guess let's show you what I mean. And we're going to start off by introducing this vocabulary word, which is the word disjoint. So two or more events, you might say that they are disjoint. This is an adjective that describes the events, or the set of events. And we only say that these two events are disjoint if they have no outcomes in common. So they're only disjoint if they have no outcomes in common. If they share an outcome between the two events, then they are no longer disjoint. As an example, suppose you're going to roll a die, and so we'll have events E1 and E2 being separate events. And so E1 is saying that you roll a number on your die less than 3. E2 is that you roll a number greater than 4. Now we can create a Venn diagram. Over here, this is VENN for Venn diagram. And what this is showing you is all of the possible outcomes are listed here, right? So rolling a 1 is one of the possible outcomes. Rolling a 2 is an outcome. Rolling a 3, of course, is one of my possible outcomes. There are 6 different outcomes from rolling a die that are possible. And what my Venn diagram shows is that E1, saying I've rolled a number less than 3, well, there's actually 2 of the possible outcomes that belong to event E1. And based on the description of event E2, there's only 2 of those possibilities that belong to E2, and notice that there's no overlap. There's none of the possible outcomes that belong to both E1 and E2. Okay, so in this case, we would see that these 2 events, E1 and E2, they are disjoint, or you might say that these events are mutually exclusive. Now here's the addition rule. If 2 events are disjoint, then the probability of either occurring is the sum of the probability of each occurring. So I'll underline these important words here. If you're asked about the sum of, or the probability that either one of 2 events occurs, and you know those events are disjoint, just find the probability of each occurring and then add that up. So again, using our same definitions for E1 and E2, if I ask you what's the probability of E1 or E2 occurring, this is going to be the probability that E1 occurs plus the probability that E2 occurs. So E1 had a theoretical probability 2 out of 6 because there was 2 possible outcomes there. And the same thing for E2. And so this total probability of asking what's the probability either E1 or E2 occurs, that would be 4/6. You could reduce that fraction to 2/3, or you could write it as a decimal like that, or as a percent like this. Okay. Oh, and there we have it. So I actually went ahead and put it on the slide already, so there we go. New example. With a standard deck of playing cards, what is the probability of drawing either a queen of hearts, an ace of spades, or a jack of any suit? So a queen of hearts is going to be this card right over here. So the queen with the little hearts in red. An ace of spades is going to be a black card right here. And a jack of any suit, well, a jack of any suit refers to these 4 cards right here. So you might label these as different events, right? So we have like event number 1, we have event number 2, and then we have event number 3 occurring. But these 3 events, E1, E2, and E3, these are disjoint. And these guys are disjoint because notice their outcomes that belong to those 3 events. They don't share any in common with each other. And so if I ask you the probability of drawing either, one of these 3 events, well, let's just calculate the probability for each of those events. and then we sum them up, right? That's the addition rule. Now, let's talk about a new example. Again, we're dealing with playing cards, but this time we ask what's the probability of drawing either a king of any suit or any one of the clubs. So a king of any suit looks like this. I'm going to circle the 4 kings in the deck in blue. But any one of the clubs looks like this. So here are the clubs across the top row. So I'm going to circle 13 cards for the clubs. Now, actually, to calculate my probability here, this is going to be the number of ways that I can count a success divided by the total number of possible outcomes. Well, if we're drawing a card from a deck, there's 52 possible outcomes. How many ways can I draw either one of these blue cards or one of these orange cards? Well, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So there's actually 16 possible ways that I could count a success in this case, if my success is drawing either a king of any suit or any one of the clubs. Okay. But, you know, we talked about how if you're talking about 2 disjoint events, then you should just be able to add up the probability of each event happening. And so, you know, for this blue event, my probability is actually 4 out of 52, which is 1/13. And you know that for this orange event, the probability is actually 13 out of 52, which is 1/4. And so if I just add these two up, you know, if I do 4 out of 52 plus 13 out of 52, as if they were disjoint events, I get 17 out of 52, and this isn't the same thing as 16 out of 52. Remember, this is our correct answer that we did, and this would then be wrong. The reason that this is wrong here is because we can't use that addition rule for disjoint events if my events are not disjoint. And so in fact these are not disjoint because I have one king that is shared between my 2 events, right? So a king of any suit or any one of the clubs, they share one card in common, and that's the king of clubs. And so if I actually want to get this right, what I have to do is take that 17 out of 52 and then subtract 1 out of 52, where that 1 out of 52 refers to that one card that belongs to both of my events. And then I would get 16 out of 52, which is the correct answer, because this way I'm not double counting that king of clubs. So with events that are not disjoint, in other words, for some events that are overlapping, it's important to make sure we're not double counting the outcomes that are in the overlap. So here's a Venn diagram again that was illustrating my example. And there are 2 events, E1 and E2. E1, containing all of the kings, has a king of spades, king of hearts, king of diamonds, and a king of clubs. And E2, notice, has a 2 of clubs, 3 of clubs, 4 of clubs, has a whole bunch of clubs cards, and that also includes the king of clubs. And so this little overlapping region, this represents the king of clubs because it actually belongs to both events E1 and E2. So know how to write this as a Venn diagram as well. And this right here, this is what we call the general addition rule, where the first addition rule, the one that was easy to remember, that only applied to disjoint events, but the general addition rule applies to any events in general. And so again, what we're doing here is taking the probability of E1 or E2 occurring, and that probability is equal to the probability of E1 plus the probability of E2, and then this is what's new, my last term on the end. It says minus the probability of E1 intersection E2. So that symbol right there is the intersection symbol here. The reason we call that an intersection, I like to think about, the streets that are right outside my office. If you have a street going east and west and a street that runs north and south, we'll call this street A Street, and we call this street maybe First Street. This area here that belongs to both A Street and First Street, we call this the intersection of the two streets. And this is kind of, maybe you're seeing a parallel too. Whenever we talk about the intersection and probability, we're talking about outcomes that belong to more than one event. Well, this little patch of asphalt belongs to more than one street, so it's an intersection. And again, on the Venn diagram, this intersection would be right here, belonging to both events. So, working our previous example, now with using our general addition rule, the probability that we draw a king is going to be E1. And the probability that we draw a clubs is going to be probability of E2. And that intersection, which represents the king of clubs, is that right there. So that's why we subtract 1 over 52 to get the correct answer that we did before. Let's suppose you roll 1 die. Now, what's the probability that you roll either an odd number or a number less than 4? Well, let's talk about rolling an odd number as being event E1 and rolling a number less than 4 as being event E2. And so let's point out that a number less than 4 would be these numbers belonging to event E2. But the odd numbers would be these, so 1, 3, and 5. Each of these belongs to event E1. So using my general addition rule, if I'm asking about the probability of getting either event 1 or event 2 satisfied, the way this is going to be is the probability of event 1 occurring plus the probability of event 2 occurring minus the probability of the intersection E1 intersection E2 occurring. So in our case, that intersection is going to be what? Well, 3 is both less than 4 and odd, and 1 is both less than 4 and odd. So my intersection is at least 2 of the outcomes. And so here, probability of E1 is 3 out of 6. The probability of E2 occurring is also 3 out of 6. But the intersection here is going to be 2 out of 6. So actually doing this calculation, 3 out of 6 plus 3 out of 6 minus 2 out of 6 is going to be 4 out of 6. And this is the correct probability here for this OR type of question. Okay, in this slide we have a contingency table. And our question for our contingency table is the question, what is the probability that a randomly selected U.S. resident is male? So here, this column is the column of all of my males. And if I want to know the probability that a randomly selected U.S. resident is male, it looks like I would probably need to do like the number of ways that you could randomly select a male, which is just going to be the number of males, divided by the total number of possible outcomes, which is going to be the total number of people, male and female. So let me get out a calculator and we can put this together really quick. So males will be 46 plus 63.3 plus 3.3 plus 12.1 plus 2.2 for a total of 126.9 males. And let's do females while we're at it. So we'll do 40.1 plus 62 plus 11.9 plus 16.1 plus 3.1. So if I entered these correctly, I now have the numbers for total males and total females. So total, I have 126.9 males and 133.2 females. And if we add those numbers up, my total number of people, adding these numbers together, is going to be 260.1. Okay. So that must be how many millions of residents that are 15 years or older in the United States, is 260.1 residents. Okay, so number of males divided by total people is going to be 126.9 over 260.1. And let's try that, 126.9 divided by 260.1. That should be, my calculator tells me 0.488, or we can write that as 48.8%. And that is our probability that we got by looking at our contingency table. Okay, new question. What's the probability that a randomly selected resident is a widow? And so for this question, we write the number of total widows divided by just, the number of total people. And the number of widows will be 3.3 plus 11.9, which is like 12, plus 3.2, which is 15.2. Then we divide by the total number of people, which was 260.1. I'm going to need a calculator to help me with this. 15.2 divided by 260.1. And that is going to be 0.058, or you might also call that 5.8%. So 5.8% of U.S. residents 15 years or older are widowed. Again, this is called what we're using here is called a contingency table. I'm just showing you how to answer some example problems that you may be asked here. Okay, if we asked about widowed or divorced, well, let's call widowed event 1 and divorced event 2. And so if we're asking about the probability of widowed or divorced, the way this contingency table is treating this is as it's, disjoint events. And if these are disjoint, then that's actually pretty nice. The probability of being E1 or E2 is just the probability of E1 plus the probability of E2. And so E1, the probability of being widowed, we just found that was 0.058. And then to get the probability of being divorced, we take 12.1 plus 16.1, looks like 28.2, out of the total, which was 260.1. 28.2 divided by 260.1 tells me that probability of being divorced is 0.108. And so we're talking about 0.108 plus 0.058, which is going to give me 0.166. So the answer here is 0.166, or we could write that as 16.6% for widowed or divorced. Now we have male or widowed, and ask yourself really quickly, this is males, so this is E1, let's say, and widowed, we'll call that E2. Well, widowed would represent these two groups of male widows and female widows. Are these two events disjoint? Well, no, these are not disjoint because we have a group of male widows that belong to both of those events, right? So we're going to have to use our general addition rule formula, which is saying that the probability of E1 or E2 occurring is just going to be the probability of E1 plus the probability of E2 minus the probability of the intersection between E1 and E2. Okay, so E1, the probability of being male, we actually found that earlier. That was 48.8%. 48.8%. Plus, we have the probability of being widowed, which we found that one earlier. That was 5.8%. And then what's the probability of lying in that intersection? Well, my intersection is just 3.3 million people out of 260.1 million people. And when I do this, 3.3 divide by 260.1, we're talking about 0.0127. Okay, adding those guys up, we do 0.488 plus 0.058 plus 0.0127. Actually, I misspoke, and I typed this in my calculator wrong, actually. Let me show you. That should be minus the intersection, so we're going to do minus 0.0127. And so the answer is 0.533, or my answer is going to be 53.3% of being either male or widowed. Now let's talk about the complement rule, and we're just going to let E1 be some event. Then we call the complement of E1, in notation, we just let a little c be on the top right of E1 to talk about the complement. And E1c is going to be the event containing all outcomes that do not belong to E1. So if this is the space of all events, or I should say all outcomes, this is the space of all possible outcomes. And then this, let's say, is the space of E1 outcomes. Then over here, this space, everywhere else, is going to be the space of E1c, the complement of E1. So when you add the two together, the space of E1 outcomes and E1c outcomes, what you're talking about is the space of all possible outcomes when you consider both of them together. So hopefully that makes sense. And the next thing we'll say about the complement is this. That whenever you add the probability of a particular event happening with the probability of its complement occurring, you get 1 because the sum of all probabilities for all possible outcomes must be 100%. And in decimal, we just say 100% is the number 1. And then the second part of that follows just by subtracting the probability of E1 from both sides of the equation. But this is nice to know. Now, let's say we roll a die. And so event number 1 is that you roll a 6. That means E1 complement is all of these possibilities, right? E1 complement. So that's basically saying that whatever possibilities, whatever possible outcomes don't belong to E1, those must belong to E1 complement. Okay. And hence, that's why those probabilities must sum to 100%. Okay, so here's a goofy question. And it says you buy one raffle ticket, and the raffle ticket is for a new set of golf clubs. And they're going to randomly select one raffle ticket out of 50. So there's 50 total raffle tickets here in the tumbler. They're going to tumble them around randomly and then just, again, close their eyes, randomly select one raffle ticket. What's the probability that you're going to lose? Well, the probability that you're going to win, well, there's one way you can win if they pick out your ticket. There's 50 possible outcomes because there's 50 tickets they might choose. So the probability you're going to win is 1 out of 50, which is like 0.02 or 2%. But we're not asked about the probability that you're going to win. We're actually asking ourselves, what's the probability that you're going to lose? But notice that losing is going to just be the complement of winning. So if we let losing, let me write this, losing versus winning. If we let winning be event number 1, losing will be E1 complement, because any outcome that doesn't result in you winning results in you losing this raffle. So we call it E1 complement. But my rule on the previous slide told me that E1 complement, that probability, is going to be the probability of anything happening, which, sorry, I should have just written 1 for all probabilities minus the probability of E1. So it'd be 100% minus the probability that you win. And that means that the probability you're going to lose will be 100% minus 2%, which will be 98%. So that's just one illustration of when you might be thinking in terms of the complement rule. And again, I hope these chapter 5 lessons are really a review for you, because I think a lot of public schools cover this material in like the middle school math classes before you're ready for algebra. And also a lot of these concepts are sort of just a little bit intuitive, or they're sort of kind of common sense in a way. Especially if you've thought about this before, you've bought a raffle ticket before, or if you've been to a casino before, maybe these thoughts have occurred to you before this class. So in any case, try not to overthink it. I know there's some formal vocabulary that you have to get used to, but it's probably not as difficult as I'm making it out to be. So have a good day, and I'll see you in the next video.